Alright, Section 7, Lagoon System. 7.1, Background. Lagoon, a pond systems used to treat a variety of wastewater from domestic wastewater to complex industrial water. Lagoon systems are primarily used in smaller communities when used with the domestic wastewater treatment system. The concept will be suited for remote wastewater treatment facilities at installations where land is readily available but skilled maintenance is not. Lagoon systems function under a wide range of weather conditions from tropical to Arctic. Lagoons can be used alone or in a combination with other treatment processes. They are often preferred system in hot climate zones where stringent effluent limitations do not need to be met. The section provides general guidance for the four major types of lagoon system: facultative, aerobic, or aerated, and anaerobic. Paragraph 7.2 provides an overview of the application of various types of lagoons. Paragraph 7.3 through 7.6 describe the procedures for four lagoon types. Paragraph 7.7 provides the design guidance for lagoon sealing procedure that apply to all lagoon types. In addition to the guidance provided here, many states' health departments have adopted detailed design criteria specifically to their geographical regions. Thus, the designer should check state regulations to determine a minimum design criteria for a pond sizing. The designer should also pay particular attention to monitoring requirements. Typical design criteria employed by engineers in the design of the wastewater lagoons can be found in the recommended standards for wastewater facilities. Great Lakes, under the Mississippi River Board of State Public Health and Environmental Managers of Great Lakes, 1990 EPA 625-183-015, design manual for municipal wastewater stabilization ponds, describes technological advances present with the detailed planning, design, construction information on lagoons, including in the Environmental Protection Agency, are detailed sample design calculations. Designers encouraged to consult with the reference design, the guidance with documentation on Water Environmental Federation MOP 8 also contains the useful detailed design information for facultative aerated lagoons. This information is also covered here for completeness. 17. Lagoon applications. Over the years, a variety of terms have been used to designate water treatment lagoons, resulting in a certain amount of confusion. Wastewater lagoon systems can be classified in dominant type of the biological reaction, duration, frequency of the discharge, extent of the treatment, the height of the pond, arrangement among cells. If and more one of the cells is used, the most basic classification describes the more biological reaction that occur in the lagoon, and classification has been adopted here. The four types of lagoon systems are facultative, aerobic, anaerobic, aerated, aerobic, anaerobic. Table 12 summarizes the information on pond application loading size for each of the pond types discussed in this section. 7.2.1 Facultative lagoons. Most common type of the pond is facultative pond. The other terms commonly applied with the oxidation pond, the stabilization of the pond, sewage of the wastewater treatment lagoon, photosynthetic pond. Facultative ponds are usually 4 to 8 feet deep, with aerobic layer overlaying an anaerobic layer with containing solid deposits. Usually detention time is very long, ranging from 25 to 108 days. Anaerobic fermentation occurs in the lower layer. Aerobic stabilization occurs in the upper layer. The key of the facultative operations: oxygen production, photosynthetic algae, surface aeration. Oxygen is used with aerobic bacteria stabilization, organic material with the upper layer. Algae present in the pond effluent represents one of the most serious performance problems associated with the faculty ponds. Faculty lagoons are widespread application. These are used to treat the municipal wastewater, usually small communities, primary, secondary effluent with the small cities. They are also used in industrial applications found in the aerated ponds and aerobic ponds to provide additional stabilization prior to discharge. The faculty of the pond is easiest to operate and maintain, but there is definite limit to its performance. Effluent BODs are values ranging from 20 to 60 milligrams a liter. Levels of suspended solids range from 30 to 150 milligrams a liter or more. Facultative lagoons require large land and area to maintain the BOD loading in suitable range for this lagoon. Typical allowable organic layers loadings are generally much higher than in summer than in the winter. The advantage in the areas with the seasonal foods processing waste are received during the summer. The total contamination of the pond and controlled discharge ponds are formed of the facultative lagoons. Total contamination pond is applicable climates where the evaporative loss exceeds the rainfall. Controlled discharge ponds have long hydraulic detention times. Effluent with a discharge once or twice per year, with effluent quality is satisfactory. Alright, aerated lagoons. An aerated lagoon is oxygen supplied mainly through the mechanical diffusion of the air aeration rather than through photosynthesis, surface, or rear aeration. Many of the aerated ponds have evaluated overlook the facultative ponds that require aerator insulation to increase the oxygenation capacity. Aerated lagoons are generally 6 to 20 feet deep with detention times of 70 to 20 days. The chief advantage of the aerated ponds comply with the faculty of the lagoon is that they require less land area. Aerated ponds are used with both municipal and industrial wastewater treatment applications. The municipal waste or aerated ponds are restored when the facultative system becomes overloaded. Minimum land is available for expansion for industrial waste. They are sometimes used pre-treatment system before discharging municipal sewage system. Both municipal and industrial applications of aerated ponds may be followed by facultative ponds. 723 aerobic ponds. Aerobic ponds are called with a high rate of aerobic ponds, maintaining the DO through their entire depth. With the detention times averaging from 5 to 20 days, they are usually 12 to 18 inches deep, allowing light and penetrate full depth. Mixing is often provided with expose all the algae to the sunlight to prevent deep deposition. Subsequent anaerobic conditions. Oxygen is provided with photosynthesis, surface reaeration, aerobic bacteria to stabilize the water. Weight table 12, wastewater stabilization, lagoon type application, typical load parameters, the typical detention times, typical dimensions, and comments. High-rated aerobic lagoons are limited to the warm and sunny climates. They are used with a high degree of the BODs removed with the desired land area limited to the chief advantage of the high-rated aerobic pond is that it produces stable effluent with low land energy requirements short with the detention times. However, the operation is somewhat more complex than the facultative pond, and unless the algae removal steps is provided with the fluent that contain high suspended solids. Short detention times also mean that they very little coliform die off while will result. Because of their shallow depth, paving and covering the bottom of the ponds is required to prevent weed growth. 724 anaerobic lagoons. Anaerobic lagoons receive the heavy organic loading, but there is no anaerobic zone. They are usually 8 to 16 feet deep, have a detention time of 20 to 50 days. An important disadvantage of anaerobic ponds is the production of odorous compounds. Sodium nitrate has been used with the combat orders, but it's expensive in some cases to prove ineffective. Another common approach is the recirculative water of the downstream faculty of the aerobic pond to maintain the aerobic layer of the surface to the anaerobic pond. Preventing transfer of odors to the air across have also proven effective with the naturally formed as with grease formed styrofoam balls. A further disadvantage of the anaerobic pond is that its effluent usually requires additional treatment prior to discharge. Anaerobic ponds are usually used for treatment of strong industrial agricultural waste or pre-treatment step where their industry is a significant contributor to municipal waste because they do not have a wide application to treat the municipal wastewaters. Anaerobic lagoons are not discussed further in this manual. Section 7.3 Faculty of the Lagoon Design. Faculty of the lagoon shall be strongly considered for those installations that have non-significant industrial water component that they have available for the land area. Lagoon is type of the simple to operate, stable to flow, and load variations, and has low capital and low operating costs. 731 Sizing based on loading of the raw sewage. Use table 13 to select values between the maximum and minimum values provided. Check depending on the severity of the freezing ice cover available. Sunshine. Check the lagoon type of the detention time is listed. Facility layout with the multiple ponds in series parallel limited with the first stage pond with the 40 pound a day acre. Kilograms per day in a hectare for odor control. In areas the average winter air temperature is 30 degrees Fahrenheit or less, the areas where the average winter area is 50 degrees Fahrenheit or greater, per cell, a series of cells may be loaded into as high as 90 pounds a day acre. Portion remainder of the total required air based on the BOD's loading with equally among the remaining cells. Table 13 faculty of the lagoon size and criteria. Climate cold, extended ice cover, minimum 15 to 20 day BOD kilogram pound a day acreage. Detention 150 to 180 days. Temperature 20 pound loading 20 pound a day acre, 50 pound a day maximum. Detention 40 to 150 days. Subtropical tropical no ice covered 50 to 100 minimum BOD loading of the pound day acreage. Detention 10 to 40 days. Depth provided with the operating depth of 6 feet, allowing the varying of the depth between 3 to 8 feet. For the following the load variations and inspect the weed control, the ponds will also slowly accumulate solids over the time. Convenient access should be provided so that the equipment can be dredged to the pond. This normally is not required more frequently than every 10 years. The design equation refer to the EPA 625-183-015 for discussing application rational design equation. Location of the lagoon is at least a quarter mile downwind of the populated areas. If the pond receives ice cover through the winter, the greater distance is recommended possible. Exposure. Choosing the site provided with the maximum sun and wind exposure. Inlet and outlets for circular and square lagoons. The inlet should be near the center for the rectangular lagoons. Place of inlet is 1/3 of the distance from the influent and locate the outlet of the short circuiting is minimized to provide outlet with capability of being drawn off at multiple depths. Construction. Provide leaves of the minimum top width of 6 to 8 feet and interior exterior slope of ratio of 2 to 1 to 6 to 1. Provide a natural impressive soil liner, bentonite clay, which is required to maximize the acceleration groundwater. Use synthetic material lining will probably make the treatment process economical. May be required for local regulations. See Figure 22 for the details about facility facultative lagoons. See refer to paragraph 7.7 for the lagoon sealing requirements. 736 layout. Using the square, rectangular, circle blades and small insulation. Single lagoons are acceptable. Multiple lagoons, large insulation range with series of parallel operations. See Figure 23 for alternative lagoon flow schematics. Recirculation can be used to increase the operational flexibility. Treatment efficiency. Recirculation returns the active algae cells. Increase oxygenation capacity. Dilute influent biochemical oxygen demand. Load. The recirculation ratio should be less than or equal to 2. 737 performance. After the TSS will vary seasonally, especially with the cold climates, between 60 to 150 milligrams a liter, more than containing 10 to 100 milligrams a liter of algae cells. The biochemical oxygen demand removal efficiencies vary essential between 70 to 95%. Orders may be transient problem during the spring and the cold climates when the lagoon surface freezes over. 7.4 aerated lagoons. The aerated lagoon oxygen-aided action surface diffused for the aeration because the solid maintains suspension while aerated lagoon. The detention time required for the biochemical oxygen demand removal will be less than 4 of facultative lagoon. The power of the requirement, however, will be greater than the facultative aerobic pond and separate settling ponds of the aerated lagoon. Affluent with usually provided with the remove the suspended solids. The aerated lagoon is operated as a complete mix of mechanically stirred, no recycling system. Compared with activated sludge system, aerated lagoons may have a low capital operating cost, great easy of operation. Therefore, separated lagoons should be strongly considered for the use of insulation where adequate land area is available for the discharge limits not restricted. 741 size basins. Number of the equal size basins provide at least 2 hydraulically separated aerated basins. Third basin with a solid liquid separation. Aerated basins should be designed to operate either with a series of parallel flow pattern. 7412 design conditions. Use more critical with the following conditions. Summer conditions where the biochemical oxygen demand load is detention period. A design the removal required for receiving water. Normal summer wastewater temperatures. One basin out of service winter conditions. Some design of the load of the summer. Same design and load as the summer. Minimum wastewater temperature removal required for the receiving wastewater. All basins in service account and anticipated ice volume and the total volume. Performance operating requirements. Detention time. Detention required for the total detention time. Given the number of the complete mixed ponds in service operation for equilibration 1, it can be used to dissolve the effluent biochemical oxygen demand of 50% of total effluency of the biochemical oxygen demand. That influent with the TSS contributed 50% of the total biochemical oxygen demand. Alright, facultative lagoon mechanically aerated operation. Alright, a manhole. You have your manhole valve of the manhole connection line for the separation operation. Influent splitter box manhole inlet and structure. Valve Valve of the manhole connecting line series operation. Drain at the pond at the bottom. Bypass effluent. Chlorinated facilities. Chlorinating building. Shear gate. Effluent pipe with a shear gate. This is continued. You have the partial flume, effluent, chlorine contact tank, bypass shear gate, effluent shear gate, flush connection, lagoon drain, valve, manhole, normal lagoon outlet, inlet structure, inlet pond pipe, bottom of the pond pipe support, minimum depth, outside diameter, maximum depth, outside area, influent, concrete splash block. D-type section A embankment, free of 18 inches, minimum liquid, minimum depth 6 foot, minimum liquid depth 2 foot 6 inches, embankment top of the width of 2.4 meters, seating of extending with an outside of the 2.4 feet above the maximum waterline, embankment, max slope, and the fences. Alright, aerated lagoons. Top of the dike, primary unit type 1 floating aerated platoon type, type 2 floating aerated donut type, effluent inlet header, stainless steel cables, bypass, control box, slide gate, chlorinated facility secondary units, influent manhole, lagoon drain valve, manhole, inlet header, influent control slide gates. 2 ponds, 3 ponds, 4 ponds, alternative lagoon flow schematic. Alright, equation T. Total hydraulic detention time divided by the divided T equally among the number of the aerated temperatures is equal to N number of aerated basin operated in series divided by KT first order reaction rate operating lagoon temperature times influent total biochemical oxygen daily milligram per liter divided by effluent dissolved biochemical oxygen daily to the 1 to the nth divided by 1. Alright, determine rates constant with the data for the actual similar wastewater operation conditions not practically used for the K2.5 day. Normal domestic water is 20 degrees Celsius. Adjusting K20, the exceeding operational lagoon temperature using equations 2 and 3. Increase the number of the ponds in series, decrease them required for the total detonation time. Lagoon temperature. Lagoon temperature is affected by the effluent wastewater ambient air temperature based on geometry mixing condition. The equilibrium temperature can be approximated with equation 2. Alright, lagoon wastewater temperature is equal to the Air Force surface area to square foot, proportional factor 12 times ambient temperature, air temperature, plus the wastewater flow rate, gallons per day, divided by times influent wastewater temperature, divided by air surface square foot, divided by proportional factor 12, plus wastewater flow rate, gallons per day. For more details, refer to the Industrial Wastewater Treatment Aerated Lagoons Advanced Water Quality Improvement that McMessany, Barton Hart, 1968, in the process design technique for the industrial wastewater treatment, Adams and Eckert Felder. Temperature correction and equation 3 with the temperature correction for the rate of the constant. KT is equal to K20, 221 divided to the 21 TL power divided by 20. Our rate of constant TL, rate of the constant 20 degrees Celsius. 0 is equal to 1.085 aerobic lagoons. Temperature of lagoon contents. Oxygen requirement. The treatment of the normal domestic sewage of the aerobic lagoons valve with 1.3 pounds of oxygen pound with applied with where the aerobic lagoons must lower the effluently biochemical oxygen demand requirements considered using the perforated pipe grid air diffusion system. Air bubble with certain current certain effects if this type of system minimize short circulation, maximize effectiveness. Lagoon valve and consideration supplier for the performance data for the alternately conserve the multi-stage lagoons effluently recycle. Alright, mixing requirement. No rational methods available to determine the proper input, but the necessary to be solved with a suspended constant. Consult with the equipment manufacturer to determine tone of the fluency of the compliance with the mixing with the vendor supplied aerator for a lagoon depth of 8 to 18 feet. Suspend the solids concentration of 1,000 to 5,000 milligram liters. Provide 60 to 120 horsepower per million gallons. Basin volume at the greater depth of the 12 feet. Draft tubes may be required for the less depths, provided with at least 30 HPs a milligram. The basin volume consult the aerator manufacturer about will need the anti-erosion assembly with a special protection features protect the pond from bottom of the front from eroding the under the efficiency of mechanical surface aerators. Locate individual surface aerators for the overlap of the zone with the influence to use several small units rather than a few large units to minimize the effect of the downtime. Or solid production buildup. Estimated production based on settable solids removed from the bottom pumps and plus the biological solids yields of the biochemical oxygen demand removal. For domestic sewage, use the 1.2 pound of the solids, suspended solids produced per pound of the biochemical oxygen demand applied. Suspend solids produced and estimate the solids build up at the final setting of the lagoon for the storage, dredging, and a period determination based on 50% of the destruction of volatile solid aerobic decomposition. Accumulated solid with a concentration of 10% provide a means of periodic removal unless the solid storage volume is adequate for the use of the life of the lagoon. 4.2 Layout. See Figure 23 alternative layouts with the multiple lagoons and series parallel operation construction. Prevent leakage of the construction of aerated lagoons with either embankments, embankments, and synthetic liners, natural soil layers. See Figure 22 for the details aerated lagoons for paragraph 7.7, the discussion of liner and ceiling requirements, dimensions. The following dimensions are minimum value of length to width ratio from 1 to 4, 1 to 1 to 4 to 1, depth of 20 to 10 to 20 feet without mixing provisions. Freeboard 3 feet. 745 inlets and outlets. Locate the inlet maximum distance for the outlet and the discharge near aeration device so the diffusion will be rapid and provide the submerged draw off to avoid the floating material and effluent. 746 protection. Provide score pads beneath the mechanical aerator to avoid any possibility of membrane liners being pulled into the aerator rotors. Provide splash box and inlet discharge wrap banks to the water surface. Aerobic lagoon design. An aerobic lagoon is most applicable to domestic wastewater treatment with the subtropical tropical climates. It should be considered for the installation of suitable land area and climate because of the simple and operative low capital operating costs of aerobic lagoons. For a continuous year-round should be restricted for the areas where the visible solar radiation is greater than 1.0 million calories per square meter per day, or 90% of the time when freezing conditions never persist for extended time. 751 sizing basis. Loading biochemical oxygen demand removed with the cell sewage and primary effluent with the aerobic lagoon can be determined by using the equation for. Equation appears first in English, then in international system in units. Alright, the BOD is 21.872 over the days. BOD equal to 6.6 over the days. BOD is removed by Laguna milligrams a liter. The lagoon D is the mid lagoon of the depth of greater than less than 1.5 feet. I is the intensity of the lagoon surface foot candles, lax flux. Term 1, determined with the method Oswald Godis and photosynthesis of the sewage treatment, ASCE 1957, in the absence of the near solar radiation data to determine the total of the required lagoon volume based on the biochemical oxygen demand surface loading rate with a 60 to 120 to the pound per day of acreage to 134. Proportion of total required volume of the equally multiple lagoons and series parallel operations. Depth. The operating depth should be 1 to 2 feet and should not exceed 3 feet to ensure the light with the penetration photosynthetic activity for full depth of the lagoon. Applications refer to paragraph Environmental Protections Agency 625-183-015. Further discussion on aerobic non-discharging lagoons and application designation equations. Design equations. Location refer to paragraph 732. Exposure refer to paragraph 733. Inlet and outlet refer to paragraph 734. And rectangular ponds. Construction refer to paragraph 373, 5, 74, and 743. Layout. For multiple rectangular lagoons and series with the parallel operation length of width of ratio of 2 to 1 to 3 to 1, and the individual lagoons should be less than 10 acres and to have maximum short. Circling cause wind action. Recirculation may be used to increase oxidation capacity. C. Influencing sewage of the algae cells. Recirculation rates of 2 tends to 0.2 to 2.0 and average is 0.5. See the figure 23 for alternate lagoon schematics. Performance criteria: aerobic lagoons are similar to those in facultative lagoons, except for the algae concentration are higher than 100 to 200 milligrams a liter for the aerobic lagoons. Aerobic lagoons should be perceived with the primary temperature for the removal of the settable organic solids. The system is not precluded not to proceed the primary treatment of influent non-degradable solids with a gradually fill the lagoon. Aerobic lagoon design. Aerobic lagoon design. Deep lagoons are received with a high-strength biodegradable organic waste such that the anaerobic conditions prevail throughout the lagoon depth. The lagoon type is primarily with treat industrial waste, generally not applicable to wastewater generated by military facility. Design guidance C APA 625-183-015. Alright, lagoon sealing. Lagoons are sealed to minimize seepage resulting adverse effect with the groundwater quality. Treatment performance. Bottom sealers are classified into three categories: synthetic rubber liners, earthen and cement liners, natural chemical treatment sealers. Naturally, sealing occurs because soil pores become physically clogged by these subtle solids. Pores become chemically clogged by the ion exchange, but the precipitation pores become biologically clogged by microbial growth. Natural setting depends on the wastewater characteristics and should not be relied on satisfying design seepage criteria. Chemical treatment sealers change the nature of the bottom of the soil. Contact the state regulatory agencies to design seepage weight and groundwater monitoring requirements for the lagoon site. Also consult the Environmental Protection Agency Municipal Wastewater Lagoon Study reports containing discussion design guidance for the minimum seepage of the groundwater. Typical design seepage rates from 10 to the -6 centimeter seconds square foot. For the domestic wastewater lagoons, industrial waste impoundments may require lower seepage rates for the double liner and redundancy. 771 Bendite admixtures. The bendite is a sodium type of the Monto-Marlenionite clay. Exhibits with a degree of swelling and previously low stability in the presence of water. It can be applied with a slurry incorporated with the soils with the sand, bentonite, and the slurry of an 8-to-1 volume ratio. This is subsequently covered with the soil. Organic polyelectrolytes can be mixed with the bentonite soil, increase the permeability of the mixture with the can attack the bentonite supply with the further information and test procedures. B. The performance of bentonite linings is greatly affected with the quality of bentonite. Bentonite characteristics should be specified with the penetration and administration, including sodium exchange capacity, percent of the silt sand and clay impurities, moisture content, particular size, and gradation. Determine the required amount of the bentonite into the bentonite soil using mixture based on the field sample, the sampling laboratory testing seal, and supply with the views of Figure 24 with the guidance only of the viewing laboratory results. 772 Asphalt cement linings. Asphalt linings may be composed of asphalt, prefabricated asphalt, with or without admixture of the bentonite or fiberglass. Soil cement sealant is the best when used with sandy, well-graded soil. Avoid using bentonite and asphalt liners in the areas with high weed growth. 773 Thin member liners. Alright, thin membrane liners. These liners include the plastic elastomeric membranes that are best used at the sites requiring essential zero permeability. Further information: CFED MCD 54 wastewater stabilization pond linings. Refer to EPA SW 870 lining waste and pond disposal facility for listing membrane suppliers and details of the construction. Alright, Figure 24 relationship with the permeability quantity for the bentonite soil mixing. Permeability of the soil bentonite mixture and percentage of bentonite dry weight soil bentonite mixture. Well graded coarse grades with a 10 to 25 non-plastic fines. Poorly graded silty sand with 30 to 50 non-plastic fines. Clay silty sand with 30 to 50% fines. Section 8 Chemical storage and handling considerations.